Hi, welcome to another edition of Linear Algebra. Today we are going to talk about the equation of lines and planes. Let's go ahead and dig out this topic. So, lines and planes. The equation of lines you have seen in high school in many formats of it. What we are going to do is that we are going to have equations of lines in xy plane again. And two ways of arriving at it: direction vectors and normal vectors. Then we are going to go to equation of lines in R3 in XYZ space. We are going to use direction vectors to get the equation, and there are several forms of equation which we are going to explain later on. Next, we are going to look at the equation of planes, of course in R3, and a couple of ways of arriving at it and several ways of writing it. At the end, we are going to talk about lines as intersection of planes. Okay, let's go back to high school. In high school, we had the equation of line in perhaps half a dozen different versions of it. Typically, some information, some points are given, and then you find the equation of the line. Central idea there was the concept of a slope. So slope was, of course, the ratio of rise to run. And the claim to fame of a line is that the slope of it is the same regardless of which 2 points you use for measuring it. So that central idea is behind all sorts of different versions of approaching the equation of line. So for example, if I was looking for the equation of this line and I was given that it passes through these 2 points, I will go ahead and calculate the slope from these two. So typically the slope is shown by a letter M, and it's found by difference of the y's divided by difference of the x's. And so here we get, say, 3/5. That's the slope. Now that slope will be the same if I measure it between a general point on the line like x, y, and either first or second point that I had. So I can go ahead and write this slope again. So again, slope between, let's call this one, say, point A, point B, and point C. This one was obtained on the line segments from A to B, and now I used, say, line segment from A to C. The slope is going to be ratio of the difference in the y's, difference of x's. Well, these two slopes are the same. That's the definition of the line, that the slopes are the same. And when you set these two equal to each other, so if I set y minus 1 over x minus 2 is equal to 3/5, well, we go ahead and simplify this equation, write it as a linear equation, and we are done. Perhaps the easiest way is just to cross multiply. So I say 5 times y minus 1 is equal to 3 times x minus 2, and this becomes 5y minus 5 is equal to 3x minus 6. And we might attempt a bit of a cleanup, so I can have 5y minus 3x, and then bringing the 5 to this side becomes minus 1. You can rearrange this in a number of ways. For example, this would be another way of writing the same thing. Any of these things will be equivalent to any other one of these things. And what we get at the end here in our textbook, this is called the general form. General form, just if you wish, that's the high school form. Ax plus by equal to c, where a, b, c are 3 numbers, is considered the general form of the equation of a line. Okay, the question is, well, what next? Of course, in high school you looked at the x-intercept, the y-intercept, double intercepts, all sorts of ways of coming to this idea. Our main angle is to look at this from the point of view of vectors. Vectors, dot products, parallel vectors, and so on. That is where we are aiming. So perhaps we can gradually build up to that by having a slightly different approach at this stage. So in high school, here was the main step to take there. So I say here, now let's consider another way of writing this equation of line. So I write this thing by cross replacing 3 with x minus 2. I'll get y minus 1 over 3 is equal to x minus 2 over 5. Just to remember where every piece came from, let me start by rewriting this x. So that was x minus 2. And what was the 5? 5 was, of course, the difference of the two x coordinates of this point. So let me just remind ourselves what that was. And then y minus 1. It's tradition to start with x and write y, but you can write it either way. Well, what was 3? 3 was 4 minus 1. So let's just remind ourselves that's what it was. So this is another way of writing equation of line. It's not perhaps as neat as this, but it's a style that is useful when you want to go to higher dimension, and actually is preferable to this type of equation. It's more to the point. So let's just paraphrase what happened here. I have x and y were a general point, and then these 1, 2, 7, 4, this was the coordinate of one of the points. So let's call perhaps one of them was point A, the other one was point B. So this is x of point A, and then here I have x of point B minus x of point A, and here y minus 1 was y of the point A, and this is y of the point B minus y of the point A. So this is the equation of the line, same as what we had before. But if you go ahead and attach z minus za over zb minus za, that's going to be equation of line in 3 dimensions. So advantage of this format is that it easily extends to any number of dimensions without having additional work. We are going to come back to that later on. So to introduce the same formula in a slightly different way, let's go ahead to the so-called vector format. So vector format, suppose we are at the point A and we want to travel on a line. To give us the direction of a line, we are going to have a so-called direction vector. So I write v as direction vector. So kind of like giving an address to a person. So go to the point A and go parallel to v. Parallel to v means what? Like let me write several components of v. So if I take one step as long as v, so perhaps this is one step, and maybe I want to take a second step, another v, maybe I want to make a third step, and so on. And of course you can take a partial step. So this way I can arrive at any point I want. So suppose I want to arrive, so I'm continuing until I arrive at the point C. So how do I arrive at C? I say, okay, start at A, go to A first, and then take so many steps, for example 3.5 steps, or as many steps as it takes to get there. The number of steps, we are going to show it by t. So that's going to be a parameter t. So here's this particular c looks like 3.5. Each time we take a step size of v. So c is equal to a plus tv. So this is playing the role of some sort of a starting point. Starting point. some point on the line in some fashion has to be given to you, and that's where it would be your starting point. So for example, that would be maybe my starting point. Of course, I could have used the other one as a starting point. If you have several of them, you can use any of them. And then instead of a secondary point, we have a direction vector. We say just walk in that direction, and the number of steps that we make, so it's step 1, step 2, step 3. So this represents t equal to 1, t is equal to 2, t equal to 3, and so on. Now that is the equation of the line. It's kind of rather cryptic because it's so short and clean and looks so different from what you have seen in high school. But that is in fact preferred to what you had over there, because this works in any number of dimensions and doesn't have any of the clutter that you see in these places, like very clean in terms of how it represents. So you have a starting point, and then you have the direction vector, and t is just a parameter showing the number of steps or number of V's that you have taken. Now if you miss your high school format and so on, you can always go back. For example, C will be a vector, perhaps just X and Y. A will be your starting point, if you wish to call it, for example, X A, Y A or something. T is, well, we said that's how many steps you are going to make, and V is your direction vector. So what how should we represent the direction vector? Perhaps by some parameters such as, say, C and D. So let's go ahead and practice this. Write equation of a line through, so exactly same language as in high school, through 3, 5 and parallel to 4, 1. So this is my starting point and this is my direction vector. So I can write it as xy is equal to start at 3, 5, and then take so many steps off, so many is t, times 4, 1. Well, what if I want to see x and y just the way I'm used to? Well, then separate. X is 3, this becomes 4t, y becomes starting 5, and then 1t. Of course, you just write that as a t. So this is referred to as a parametric form. Because you see the parameter t here. This one, due to the fact that these are all vector ingredients, is called the vector form. This is also the vector form because you see these in separate pieces in shape of vectors. So in WebAssign it asks for vector form, probably wants this one. Well, how about the other one that we advertised here and said it's closest to what you had in high school? How do you get these things if you want? Or what if the problem asks for that high school format of general form? Where do we go? Well, calculate t from in these places. So from first equation you have t is equal to x minus 3 over 4. From the second equation, same t is equal to y minus 5 over 1. So this equation that we have is exactly this style, or what we had, more or less something like what you had over there. Then you go ahead and simplify this. So forget about t now, just concentrate on x and y. This is sometimes referred to it as eliminating t between these two equations. So you cross multiply, so 1 times x minus 3 is equal to 4 times y minus 5. So x minus 3 is 4y minus 20. And then we can write, for example, x minus 4y, and that equals to minus 17. And we can do other simplification to this, but this is just as good as we need. This is going to be called the general form. Okay, now we said we have a long list of things to go through. So what we did here, we talked about the direction vector going in direction of a certain vector. Sometimes instead of going parallel to a vector, you want to go at a certain angle. The most useful angle is of course going to be 90-degree angle. So here is lines in R2 using normal vector. This is also a format that you see in high school. Sometimes they say I have a point here and I have a line or a vector. Tell me equation of a line that goes through this point and is perpendicular to that line. So sometimes we want to find this line, we want to find that line so that it will be perpendicular to a certain vector. So let's go ahead, write the general form of this thing. Suppose this is, again, they almost always give you a specific point to work from, and then we have a normal vector. Let's call this thing n so that we remember it's normal to something, and we are after the line itself. Well, what do? Go ahead, pick out some general point on that line. General point again means x and y, whose relationship we are going to be finding. Well, what now? Well, you have this this vector, which is what? Which is perpendicular to this other vector. So what was the condition of perpendicularity? It was that the dot product is 0. So the vector AC, if you dot it with n, you get what? You get, of course, since they're supposed to be perpendicular, of course we have to get 0. Well, then what? Well, that's actually the equation. We are done. Again, it looks deceptively simple. Are we done? Yes, this is our vector form. Now, to make it a bit clearer, remember AC, going from A to C, that vector is C minus A. So if I have this origin here and I had be given coordinates of A and coordinates of C, then the line that goes from this end to that end is C minus A. C minus A will be dotted with n, and it's going to give us R0. Again, it's a bit unsettling because we are used from high school to seeing x's and y's all the time. If you insist, let's go back there. So C is what? C is x and y. We write it as a vector. So x and y. A is some starting point whose coordinates are given to us. So xa and say ya. So we have to subtract these two vectors. And then dot it with n. So n, whose coordinates will be given to us from somewhere. Again, let's just for right now, just call it, say, C and D. That has to be, the dot has to be equal to 0. Well, how did we do the dot? First, do a subtraction. So it's x minus xa, y minus yb, and then this is dotted with C and D, and the dot product is 0. Well, when you multiply them, what do you get? First with first, second with the second, and then you have to add them up. C times x minus xa, and D times y minus y. Excuse me, I made a mistake here. Let me go make the correction. This was supposed to be A. Starting point called A. That has to be 0. Well, simplify it. Something times x minus that thing times xa, some number times y minus that number times ya has to be 0. X and y were for the variable point c, so let me put them next to each other. Cx plus dy. If you wish, take these two other to the other side, becomes cxa plus dya. So what do we have now? Cx plus dy equal to, well, this is some number, and that we have arrived at what again we called in high school this general form. This is going to be the vector form. So if you write it like this, because you were spelling out the vectors for yourself, and if you convert it to however it was in high school, let's go ahead and practice thing. Find equation of line through, again let's say 3, 2, and normal to, meaning perpendicular to another vector. Let's use some other numbers, say 5 and 7. So that is like that point A there. This is our normal vector A. So we write x minus 3, y minus 2. So that is the vector from A to that generic point C, dotted with the vector 5, 7 is equal to 0. So that's the vector form. Vector form using the normal vector. Of course, you can multiply this thing. 5 times x minus 3. So it becomes 5x 7y. 15 and 14 becomes 29. So that becomes general form. Okay. So far, it might look like we didn't make much progress because we're still in high school. We're writing equation of line, but we practiced both versions of it. Well, it's going to be quick for us to do lines in R3. If we want to do it with the direction form, so let's write equation of lines in R3. So how do we go here? We are in a three-dimensional space. As before, we have some starting point A. We have some vector V as our direction vector or guide vector, and we are going to go in that direction. So we can do 1V, 2V, 3Vs, 4V, and so on. That is going to be our line. How do we find that equation? So as before, just pick some general point here, C. How do I get to C? Start at A, take so many steps, and that's it. So let's go ahead and practice. Find equation of line. Now what's different is that we have three pieces, as I say 2, 3, 4, through. So some starting point is given, and parallel, so a direction vector is given to us, V. Let's use some other number, say 5, 8, what's good, say 1. So how do we write the equation? So C is x, y, z. Start somewhere. So this is through. So it starts at that, and then take so many steps of this. T times 5, 8, 1. So that's going to be the vector form. If you separate it, x is 2 plus 5t, y is equal to 3 plus 8t, z is equal to 4 plus 1t, or just t. This is going to be parametric form, because t is kind of standing out. If you want a symmetric form, calculate t from all of these things, set them equal to each other. So t becomes x minus 2 over 5, y minus 3 over 8, z minus 4 over 1, and they just don't mention the t anymore because it's not playing much of a role. This is going to be called symmetric form. Now, of course, you can cross multiply and write it as two separate equations. That's just as well as would be one more form. Maybe we name that after you. So that's the equation of the line. We are not going to have the normal form here because if you have a line and you want to write a line perpendicular to this, you have infinitely many choices. They all constitute the whole plane. So the normal form does not get to be mentioned here unless you have additional information. So that was it. That is the equation of lines in R3 and all the forms of it. So we are done with that. Equation of planes, and of course we have to be in R3 to talk about that. Otherwise in R2 it's just one plane, which is R2 itself. And so equations of planes in R3. Well, it's going to be a little bit hard to draw this thing. Easiest way to visualize such planes is through their intercepts with the axis. So if you have a plane and it does intersect right here, you have an easier way of looking at this thing. So if you have, say, x, y, z, you can sometimes talk about the x-intercept, and then of course y-intercept and z-intercept. X-intercept means what? X-intercept means y is 0 and also z is 0, because you are right on the x-axis, there's no y or z, and so on for the other ones. Another way of flagging these kind of lines is through the so-called trace. So I could like this is going to be a trace on YZ plane, meaning once the plane cuts that other plane, well, they're going to cut at a certain line, you kind of flag it out and you have a trace. So sometimes we talk about intercepts, sometimes we talk about trace, whatever is convenient. Well, how would you give the equation of a plane in R3? Easiest way is through the normal to the plane. This plane will have a family of vectors that are perpendicular to it. So here I draw something. You have to imagine that this is perpendicular to this plane. Well, if I know the normal vector, so this is going to be my normal vector. If I know this normal vector, how do I get the equation of the plane? Well, as usual, I need some handle to work with. So some starting point, something. So suppose we want to find the equation of plane through, so easiest way to get started is to say what the plane goes through. So I give some coordinates, say A, and perpendicular normal or orthogonal, we said several different words, to some vector n. Well, how do we do that? So again, let's go ahead and pick some other general point. Let's call it point C, and we say that, well, if n is normal vector, then it's going to be perpendicular to every vector on this plane, and in particular it's going to be perpendicular to this AC. So N is perpendicular to AC. So how would I write this thing? So point C is some general point, which we call it just X, Y, Z. Starting point, as before, is like XA, YA, and ZA. That's going to be perpendicular to vector N. So I write this thing as AC is, you remember, as just like the last time, AC is C minus A. It's just like what we had. If I have a point A and I have a point C, I want to go from one to the other. That vector is simply the difference of the two location vectors of A and C, C minus A. Exactly that formula is going to be here. So C minus A dotted with N is going to be 0. Let's go ahead and write a simple example for this. Then you can generalize it to this format. So suppose we want to find equation of plane through, okay, so let's say 2, 3, 5, and normal to, let's write some other numbers so we don't get mixed up. Let's make it 6, 6, 4, 7. So that plane is made of points with coordinates x, y, z. We take that, that's my C. Subtract my starting point from it. So x minus 2, y minus 3, z minus 5. So that is my displacement vector. It's normal to this. So normal to that means, well, if I dot it with that, I get 0. Well, we are already there. This is the vector form of the answer I want. Vector form. Well, if you insist, well, I want to write it in a way I'm used to from previous classes, well, dot them. So it becomes 6 times x minus 2, 4 times y minus 3, 7 times z minus 5, whole thing 0. So let me multiply the first round, 6x, 4y, 7z, bring everything else to the other side. So 12 and 12 and 35. So that's what? That's 59. Notice the multiples of x, y, z are just proportional to my normal vector. That's always the case for a plane. You can always look at the equation of a plane and extract the normal out of it by just picking the multiples of x, y, z in that order. From here we learned something, that the equation of a plane is always turns out to be some number times x, some number times y, some number times z, and pile everything else into one number. That is going to be general equation of a plane. So in that case, our general equation 6x plus 4y plus 7z is equal to 59. And once again, let me remind you, the normal to the plane from that equation is very easy. We don't need any work. We just harvest these three numbers. That vector or any multiple of it is going to be the normal vector. Okay, that was a very easy way of getting the equation of a plane. Every now and then something a little bit more advanced might be presented to us. We might have a plane, and we might think about this idea of for a line we had the direction vector. We might ask ourselves, well, how about planes? Do planes have direction vectors? Well, yes, they do. It's just a bit more complicated because there have several of them. So I might be on this plane. As usual, I start from some starting point A, and then just like a city, you can go on the avenues, or you can go on the streets. So I can have one direction vector, or let's see, or some other direction vector. So I might tell you go several steps in direction of V, several steps in direction of W, or a combination of them. For example, if I tell you go V and then W, or W and then V, well, you arrive at this point. If I tell you, well, take 2 steps in direction of V and then 1 step in direction of W, or W first and 2 steps, well, I'll be here. Well, what if I tell you go 2 steps in the direction of W and then 1 step in direction of V, you'll be here. Or 2 and 2 brings you here. So gradually you start forming something like city blocks, except that these streets are not necessarily perpendicular to each other. So you get something called the lattice, kind of like a tile work that you might see in some section of a building or something. How do we arrive at some general point C here? So, well, say start from A, take so many steps in direction of V, and so many other steps in direction of W. So this is the starting point, some point, starting point. This is one direction vector, and this will be another direction vector. And you can take as many of the first one, as many of the second one as you want, and then you arrive at your final destination. So that's going to be equation of a plane with 2 direction vectors. So this is equation of a plane given 2 direction vectors. I'm going to leave it to you to figure out how do you go from this one to that one. So let me leave that as a little challenge for you guys to work on. Okay, so we talked about the equation of planes in R3, 2 different forms of it, and normal work, and a pair of direction vectors. We're done with that. Lines at intersection of planes. Let's talk about that too. And this is a bit of a lengthy section. We're still more stuff to talk about, so I'll postpone that to another lecture. So the idea here is that if I have a plane and then another plane, well, they could have a visible intersection, which is a line, just like you see a standard situation where 2 walls intersect, or pages of a book intersect at their spine of the book, and so on. So one way to describe a line as intersection of 2 planes. So you can plane number 1, plane number 2. You have some intersection, and a variety of questions could be asked in that context. Let me find an example from your Sorry for that, I thought I saw a problem of that style in the book, but let's just make it up. So I have the equation plane number 1. Suppose this has equation, say 2x plus 3y plus z is equal to, say, 1, and another equation for the other plane, suppose x minus y plus 2z is equal to 3. The question is to find the description of the line that is at the intersection of the two of them. So let me write the two equation. X minus y plus 2z is equal to 3, and then 2x plus 3y plus z is equal to 1. So let's call this thing plane A, plane B. So this was my plane A, this was my plane B. So the points that are sitting on this line, well, they are in both planes. So the x, y, z of this satisfies both of these equations. So x, y, z of this satisfies a system of equations. So this is a first example of a system of equations. You remember in the first introductory lecture we talked about systems as a manifestation of interaction of particles in an environment. But now, well, we are looking at point of view of geometry. X, y, z are coordinates of planes in a space, and when they intersect, this x is same as that x, this y same as that y, this z is same as that z, because that is shared to both planes. Okay. The question is, how do I get my line? I want the line of intersection, and for a line we had several forms of equation of a line. You get a vector form, symmetric form, whatever you want. So we have to make it look like that. Let's go for, say, parametric forms. Now when you look at this system, something might be slightly unsettling for you. It's like, okay, if I have 3 variables, I need 3 equations to get a number. But remember, we are not looking for a specific number. Rather, we are looking for description of all of these points. So it's not that we are expecting that you find x, y, z as a specific number. If it were so, you're choosing a specific point on this line. Rather, we want to find all of them. So that's where the parameter comes from, and that's why this equation is a little bit unfamiliar. There are more variables than there are equations, and that means likely we are going to have a parameter that solves this. So how do we do this? Well, the style of solving it, we are going to talk much more extensively about this thing later on when we talk about matrices and so on. But right now, whatever you learned in high school is enough for handling this. For example, what I can take the z to the other side. So first of all, to bring that parameter t to my equation, it's customary to go ahead and call z to be that parameter t. So I call z to be that t. Next, I take the z and take it to the other side, so it becomes x minus y is equal to 3 minus 2z, which is now is going to be minus 2t, and this is going to be 2x plus 3y is equal to 1 minus z, which we agreed we call z to be t, so that our parameters explicitly mentioned. So my system now looks like this. Now, aside from the fact that on this side you have some parameter, this is exactly what you have seen in high school probably hundreds of times. How do you solve this system? You can do elimination, substitution, or whatever you want. Let's just do elimination. Suppose I want to eliminate y in this pair of equation. What do? Multiply this thing by 3 and add up the two equations. Now minus 3y and plus 3y are going to cancel each other out, and I'll be done. So when I multiply the first equation, it becomes 3x minus 3y is equal to 9 minus 6t. Second equation becomes 2x plus 3y is, well, whatever it was, minus t. When you add them together, magic is that the y's cancel out. That's why we did this. The y's cancel out, and you get what you get. You get 5x is equal to, this is 10 minus 7t. So we can say x is equal to 2 minus 7/5 of t. Now you can take your x here and plug it back in either of these equations and catch your y if you want. Or you can go back here and repeat the process for elimination. For example, you can take, so we can take this equation, first one, multiplied by minus 2, so that when I add them, x's cancel out and then a y comes out. So two options. You can go another round of elimination, or you can take x here, put it there, and figure out y by substitution. Either way. So let me continue this thing. So it becomes minus 2x plus 2y is equal to minus 6 plus 4t. Second equation was 2x plus 3y is equal to 1 minus t. When you add them together, we get 5y is equal to minus 5 plus 3t. And so my y becomes minus 1 plus 3/5 of t. Okay. It's a good idea to go check what we have. For example, let's go check x and y in either of these two equations, make sure we are on the right track. We had x minus y, let's repeat, 3 minus 2t. So I'm just checking to see my arithmetic is okay. My x was 2 minus 7/5 of t. My y was minus 1 plus 3/5 of t. When I subtract them, 2 minus minus 1 is 3, and minus 7 minus 3 is minus 10/5 of t, which is 3 minus 2t, which was what it was supposed to be. So I'm more confident that I'm on the right track. Let's go ahead and put everything in a box as to, well, what did we find? We found that x is 2 minus 7/5 of t, y is minus 1 plus 3/5 of t, and z is equal to t. So that's the equation of line that is sitting at the intersection of those two planes. So we learned how to find the intersection of two planes. We learned how to solve a peculiar looking system of equation. It has two equations, has three variables. We had to kind of play around with it to get our answer. Our answer here came out in the parametric form. Okay, you're going to have quite a few exercises in this section, and we are still halfway for this section. We still have to talk about the concept of a distance. So next lecture is going to be, well, so far we have talked about points, lines, and planes. Okay, in college algebra you have a distance formula. Is that right? You have a distance formula, but that's not just for planes. Now we are going to go one step further. So you can have a point and another point, you are finding the distance. You can have a point and a line and you are finding the distance. Or you can have a point and a plane and you want to find the distance. And other variation on these themes. So distance between points. Okay, so that is the high school. That was distance formula. Between a point and a line. What do you mean by distance? Well, that means shortest distance. Always distance means shortest distance. What's the shortest distance? Same idea here. Between point and a plane, okay, so these ideas, let's postpone it to the next lecture. Until then, good luck and God bless.